So when an electrical discharge passes through gaseous hydrogen at low pressure, electromagnetic radiation is emitted. Indeed, that's an emission spectrum. Describe the processes that cause the electromagnetic radiation to be emitted. Well, I've already done that once and skipped it once. So it's 3 times in 6 years that that particular question has come up. In other words, be sure you know how to describe how you get an emission spectrum. Now, the electromagnetic radiation is passed through a spectrometer. Several series of converging lines are observed. Why are there several series? Well, we've got electrons move from higher to lower levels. Okay, so let's do this, and there's different possible ending levels, and it's those ending levels that give rise to the series of lines. For example, let's imagine that we had some electrons in hydrogen. Some of them are in the 5th, some in the 4th, some in the 3rd, some in the 2nd level. Well, these can emit the appropriate photon to get down to the ground state, to the 1st level. So that would be one series of lines, these particular energies from that one, that one, that one, that one. On the other hand, though, who's to say that all of the ones that started off in the 5th level end up in the 1st level? Some of them could go to the 2nd level, some in the 4th could end up at the 2nd level, some at the 3rd can end up at the 2nd level, and this is another series of lines right here. Why do the lines within each series converge? Well, because the energy levels get closer together. Let's look at the n equals 1. Okay, you've got this energy here, that one there, that one there, that one there. And if you look at, because these energy levels are getting closer together, so the differences between the energy levels and n equals 1 are getting closer together. So this one here compared to that one here, this one here is certainly not twice as big as that one, and this one isn't 3 times as big as this one, and this one isn't 4 times as big as this one, as you would expect if the energy levels were equally separated, because the energy levels get closer together, so the differences in energy between those levels and the ground state, or between the 2nd state and so on, those differences get closer together, and those differences of course correspond to the energies that are emitted. So electrical discharge passed through gaseous hydrogen at low pressure, we're going to get the emission spectrum. Now the convergence limit of the Lyman series of lines occurs at a wavelength of 91.2 nanometers. Well, what does that convergent limit represent? Well, first of all, the Lyman series is where we're getting wavelengths associated with n equals 1. So if it's an emission spectrum, that's where the electron that's been excited to higher level ends up at n equals 1 after it's emitted the appropriate photon. Okay, now these wavelengths converge at n equals infinity because they get closer and closer and closer together, because if you remember, the energies of each of the energy levels get closer and closer and closer together. At n equals infinity, the electron has gone, and that is the ionization energy. Okay, so this limit, right, the convergence limit at the wavelength of 91.2 nanometers, that's where all of them get closer and closer and closer together and end up really close to 91.2, and that is represents the electron gone, which is the ionization energy. Now we'll calculate the energy, and of course I did a lot of these calculations on the other atomic structure worksheet, but that's right, we'll go through a few of them. We know a couple of relationships. The first relationship is the speed of light, 3 times 10 to the 8 meters per second, is equal to the wavelength times the frequency. And here I'm using the A-level symbol needed, F for frequency. Okay, pop in our values. We've got 3 times 10 to the 8 meters per second for C. Lambda, we're told, is 91.2 nanometers, and frequency's what we need to get from this part of the calculation. Big problem, of course, we've got nanometers here, meters here, so we need to convert nanometers to meters. Nano, of course, means 10 to the minus 9. So we get 3 times 10 to the 8 meters per second is 91.2, was nanometers, now times 10 to the minus 9 meters. Rearrange that, we get the frequency is 3.29 times 10 to the 15 per second. Now, that's the frequency, but we wanted the energy. So we look at the second relationship. Energy is H, that's Planck's constant, 6.63 times 10 to the minus 34 joule seconds times the frequency. pop in what we got. There's the frequency we calculated, 3.29 times 10 to the 15 per second. E is 6.63 times 10 to the minus 34 joule seconds. So when we multiply this out, the seconds and the per second will cancel out, and we get 2.18 times 10 to the minus 18 joules. Now, that's the energy of a photon. But we don't want a photon, we want a mole of photons. So we have to calculate the energy for a mole by taking the energy per photon, multiplying by 6.02 times 10 to the 23, and we get this ridiculous number here. However, the question also said not joules per mole, but kilojoules per mole. So we'll divide this by 1,000 to turn from joules to kilojoules, and we get 1,312 kilojoules per mole. Mandelenitrile is a yellow material, give the appearance of mandelenitrile when viewed under a blue light, giving a reason for your answer. Well, if it's yellow, that means that it has absorbed effectively, nice and simplistically, blue light. You have this nice little color wheel where whatever color you see means that you go 180 degrees across or directly across the color wheel to see what light was absorbed. So because we see yellow, that means mandelenitrile absorbs blue light. Well, now, if we've just got blue light being shone on it and it absorbs blue light, well, then all the light is absorbed. All the other red, green, yellow and stuff's not there because we're looking at it under blue light. It absorbs the blue light. So when there's all light is absorbed, something looks black. Same idea here. Complete the gaps in the following sentence, choosing from the words blue, yellow, higher and lower. So benzene is a colours compound that absorbs energy in the ultraviolet region of the electromagnetic spectrum. Jolly good. Nitrobenzene is a yellow compound. Well, if we see yellow, that means that it absorbs blue. Okay. Now, the absorption of energy for benzene occurs at an energy and frequency than that for nitrobenzene. Well, benzene is ultraviolet. Nitrobenzene absorbs in the visible. Ultraviolet has a higher energy and a higher frequency than the visible. DEET is a colours compound in white light. Explain in terms of the spectrum why DEET is colourless. If it's colourless, it means it doesn't absorb any of the visible electromagnetic radiation. Here I'm giving a bigger range than the A level, 360 to 750 nanometers. This is a more realistic range. A level, 400 to 700, tomato kind of thing. Table C is the colour seen and absorbed for a solution of mordant orange 1 as the pH increases. State how the wavelength of the light absorbed changes with pH. So here we got pH increasing, starts off absorbing violet and ends up absorbing greenish blue. Well, here is the electromagnetic spectrum. As we go from left to right, the wavelength increases, right to left, the frequency increases, but we don't care about here. So what that means is that violet has got the lowest wavelength all the way up to dark red, having the highest wavelength. Well, let's see what we've got here. At this lower pH, it's violet. Higher pH is this greenish blue color. So therefore, wavelength is increasing going this direction too. So as the pH increases, going that direction, the wavelength also increases as we go from violet with the low wavelength to greenish blue with a higher wavelength. Looks like the same question, but now I'm moving into part 3. The visible spectrum of the dye at pH 10.1 shows it has an absorption at 385 nanometers. Calculate the frequency of the radiation absorbed at 385 nanometers. So again, we're using this relationship here. We've got a wavelength, we want a frequency. The relationship between them is 3 times 10 to the 8 meters per second. Pop in our values. Notice again, this is nanometers. We don't want nanometers, we want meters. So replace nano by 10 to the minus 9. Rearrange it, and we get the frequency. And then it says use our answer to 3. So we hope we got it right. To calculate the energy at this point, well, energy relates to frequency using E as H times F. So the same kind of calculation that we've done before. Energy is 5.17 times 10 to the minus 19 joules when we pop everything into the Planck's equation. Trouble is, of course, this is joules per photon. Doesn't want per photon, it wants per mole. So we multiply by 6.02 times 10 to the 23 to give us joules still per mole. It wants you kilojoules per mole, so divide by 1,000, we get 311 kilojoules per mole. Do note this, that at least up till now, the A level really is into the kilojoules per mole. So once you've used this equation, E is H times frequency, you have to do two more things, turn it to per mole, and then turn it to kilojoules. Maximum absorbance for our zero occurs at 518. Calculate the energy of this absorption. So again, same thing. We're given nanometers. We want energy in kilojoules per mole. So we have to put in to the C is lambda times F. Remember, nanometers, change the nano to 10 times minus 9. Get the frequency by rearranging that. It's just 3 times 10 to the 8 divided by 518 times 10 to the minus 9. Once we got the frequency, pop it into the energy relationship. So multiply the frequency by Planck's constant. And we get this value, which is per photon. Turn it to per mole. Turn it to kilojoules per mole. Visible spectrum azo dye at certain pH says an absorption maximum at 410 nanometers. Calculate the frequency. Are you observing a pattern here in the kind of questions they're asking? C is lambda times F. Again, pop it in, change nano to 10 to the minus 9. And we get the frequency 7.32 times 10 to the 14 per second. Always useful to get a feel for the appropriate size of your answers. Frequency, when we're talking about all of these things, is going to be 10 to the 13, 10 to the 14, 10 to the 15. If you don't get a big number like this, you've done something wrong.